And this, of course, the question should also be recorded. Yeah.
Okay, so my question is, while finding out the VO by VI ratio and plotting it, why are we considering the modulus of the complex number and not the real part?
Okay. So I hope everybody can see this, right? The sheet of paper.
Yes.
Oops. You could, but you can't now. Let me just. There's something wrong with this button, but anyway. Anyway, you can see that there is a piece of paper here. As I kept on saying, VO and VI, both of them actually, if you look at the real time dependence, there was some constant, let's call this A for the time being, cosine omega t plus phi plus delta, whereas VI, a function of time, was some other constant B, cosine omega t plus phi, right? So this was the scenario. You had a VO, you had a VI, and they were basically functions of time. They were cosine functions of time, right? Now, what we did was we said that, okay, these are real parts of complex numbers. So the real part of B and after a while what we did was simply forget about or pretended to forget that we were dealing with real parts of complex functions and then said something like VO of t is not the real part of anything, it's just A tilde, it's a j omega t plus phi, where A tilde of course is A e to the power j delta, and Vi of t, the input, the same time was B tilde to the j omega t plus phi. So B tilde here of course is simply the number B. Okay. So when I want the ratio of the two output to input ratio to find the gain, what should I really find the ratio of? The actual amplitudes or the complex voltages? What do you think? That is, should I take the ratio of this amplitude A here with B here and call that the gain?
So wouldn't it be the same because it's just a phase factor?
Well, it wouldn't be because it's just a phase factor, but it's a phase factor, right? So if I just divided these two, the complex voltages, which I'm not, okay, I should, since we are on the same page, at least we should write the complex voltages with tildes. Just remind ourselves for the time being that they are complex. Okay. Later on, we just keep on using complex voltages all the time, so we don't even make the distinction. So we should write V0 tilde by Vi tilde. That of course is A tilde by B tilde, and that is A by B into the J delta, right? Now, which one of the two do you think is the actual gain? Is A tilde by B tilde the gain or A by B the gain?
A by B cos.
A by B is the actual gain, right? The maximum size of the output voltage, that's A. The maximum size of the input voltage, that's B. The phase shift delta really tells you that these two maxima may not occur at the same time, right? But ultimately, what is the largest value of the output you get? That's the size of your output. And that's the largest value of input that you have. You should take the ratio of these two. This A by B ratio is what you call the gain, right? I'm not saying delta is useless. Delta actually has a huge amount of information. It tells you what is the phase difference between the output and the input. It tells you which one is leading, which one is lagging, and so on. So, in fact, when you divide the complex output voltage by the complex input voltage to get this A tilde by B tilde ratio, this complex number has both informations. It has the information about how big the gain is. It also has information about what is the phase difference. But A by B, which is what you call the gain, which is the output amplitude by the input amplitude, is actually the magnitude of A tilde by B tilde, right? If you take the magnitude here, A and B are real numbers, so the magnitude, the ratio of course gives you whatever. Just if you take the magnitude, you will get A by B. Because J delta has magnitude 1. On the other hand, if you took the real part first and then took the magnitude, you will end up with then took the ratio. You would actually end up with a time dependent factor, right? Because you'll be taking the ratio between A cos omega t plus phi plus delta by B cos omega t plus phi, and you will get something which fluctuates rather widely. In fact, goes all the way to infinity even when the cosine omega t plus phi goes to 0. And delta, of course, because of delta, the VO will not go to 0. So that's not a very useful quantity. So what I'm saying is A tilde by B tilde is actually what we often call VO by VI. Okay, the complex ratio. And the complex ratio has a lot of information. It has the information about how big the gain is, as well as its phase tells you what is the phase shift between output and input. You don't want to give up on any of that information. Both of that pieces of information are important. However, when you say just gain, you mean A by B, and that's magnitude of A tilde by B tilde. Does that answer your question?
Yes, sir, but last week also I asked you the same question, and in the circuits which were done previous to that, so I was actually confused as why we were not taking the complex amplitude. So you said that just because it was the input is real, so we need to consider the real part even after the out.
Yeah. I'm sorry if my two answers seem contradictory. Look, the input is this, B cos omega t plus phi. That's always the input. Okay, the output is this. So the actual output and the actual input are always real functions. They are not complex numbers. Okay? The complex functions that we use are simply used for our, say, ease of calculation. The ease of calculation, apart from being the fact that calculus is easy to do with exponentials, also tells you the fact that if you take the VO tilde by VI tilde ratio, the complex voltage ratio, the ratio that you get is a constant complex number, a time independent complex number, which in itself has both the pieces of information. It has information about the magnitude and the phase, and the magnitude ratio of the A tilde by B tilde is actually what we call the gain. The gain is simply how big, what is the maximum value of the output by the maximum value of the input, right? As long as, that's of course how you define the gain. The gain is not output by input, because the output by input of course fluctuates badly with time, right? Unless of course there is zero phase shift between output and input, the output input ratio will be another complicated function of time, and dropping to 0 at times, shooting off all the way to infinity at times, jumping from plus infinity to minus infinity, and doing all kinds of crazy things. That's not what you call the gain. And anyway, when you measure the output or the input, suppose you have an AC signal, when you measure the voltage, very rarely do you actually measure the instantaneous voltage. What you usually measure is either the peak to peak voltage, or the peak voltage, or the RMS voltage, each of which are actually either A itself or twice A or A by root 2, something directly related to A, right? So if you take the convention that you are always going to use the RMS voltage, then again the ratio of the RMS voltage is actually A by root 2 by B by root 2, which again turns out to be A by B, right? So it's A by B which you really need to call the gain, and not A tilde by B tilde. But once you calculate A tilde by B tilde, you just take the magnitude, and that gives you A by B. The only possible further scope of confusion is, I have been rather pedantic here and written down VO, VI, and been careful to write VO tilde and VI tilde whenever we have talked about complex functions. But usually we are not that careful. We don't write VO tilde for the complex function, we just say VO. And we assume that when you see that VO is a complex function, you know that that's really not the output, its real part is the output. Okay.
Yes. Thank you.
Okay. Any further questions?
Hello, sir.
Yeah. Who is
Yeah, I
this?
have a question.
Could you just identify yourself? I can't see the screen right now. So,
I'm Shashank, sir.
Prashant, yeah.
So when we say VO, we actually mean like we are trying to attach some other component to it, and we can use that voltage, right? When we say VO, but then when we attach some other component to wherever we want to draw that VO, that will change the impedance of the circuit, and hence
Of
the
course. So when you say VO, that depends on what you mean. It be say you are talking about RC circuit, and say this is the VO for the RC. Okay. Let's say your circuit is like this: R and C, and you want to find out the VO for this. And you have VI here, some kind of sinusoidal signal, and you want to find the output for this. Now, what you are saying is, if you were to connect something to it, then of course the impedance of the circuit will change. Absolutely. However, when we say output of the RC circuit, we mean the output without connecting anything to across the C, or well, if you don't connect anything ever, you will not even be able to measure what the voltage across the capacitance is, or at least assume that you have a very, very high impedance voltmeter or some other device which can measure the voltage without affecting it substantially. So when you say VO for the RC circuit, of course you mean without anything else connected to it. If you connect something to it, its VO is definitely going to change. Okay,
sir. But
and
then
if you measure something, of course, that of course has nothing to do with electronics. That's where everywhere in physics, whenever you measure something, you are actually disturbing the system. You want to measure the temperature of a body, you're connecting it to a thermometer, right? The thermometer will take up some of the heat, so it should reduce the temperature of the body by a small amount, reduce or increase depending on whether the thermometer was initially colder or hotter. Okay, but the idea is, by choosing a good enough instrument or an instrument which is subtle enough, you should be able to measure the output voltage in this case, or the output current if you were measuring currents, or temperature if you were measuring temperature, without disturbing the system too much. Thankfully, we are not doing quantum mechanics here, so you don't have to bother about system measurement disturbing the system too much. Of course, if you connect something else to it, let's say you connect a resistance to it, some other or other inductance or whatever, that will be a different circuit altogether, and that will have a different output impedance, even output voltage. That's of course true.
So, but then when we calculate the omega, which it will pass as a, like when it acts as a filter, that omega will also change, right?
Of course.
So, I mean, then we should
Provided that's true. So what we do is that is the loading effect that you're talking about, and that's exactly correct. Except that very often, in most practical situations, what we have is that the impedance provided by this RC network is much smaller than the impedance of whatever you connect to it. There is a very, very good approximation to ignore whatever you connect to it for the purpose of just studying the frequency response. So you will see plenty of examples of this happening all the time. That is, in real circuits, whenever we use this, can we ignore the fact that something is loading the circuit? The answer is yes or no, depending on how much loading you are providing. If RL is very big, it will really not make much of a difference. Say, you also know one thing, right? When we say you have got to the half power frequency, that means the impedance of the capacitor 1 by omega c is exactly equal to the impedance of the resistance at that point, right? That's the omega half power frequency. Okay? Now if RL happens to be much bigger than 1 over omega 0 c, which of course means is much bigger than R in the circuit, then whether you're whether you're connecting the RL or not will not make much of a difference. See, if RL is 10 times 1 by omega 0 c, then only 1/10 of the overall current will flow through RL, the rest will flow through the capacitor. So, depending on how precise you want your answer to be, you might be able to ignore RL. If RL is 100 times 1 by omega 0 c or 100 times R, then you can definitely ignore RL. Okay.
Okay.
Now, I'm not sure whether you heard my sermon at the very beginning of the course. One reason why electronics is very important as a course is that it exposes you to the realities of doing physics. That is, despite the fact that there is really engineering and not physics, it's about the only part of your physics course which deals with approximate answers and considers that to be a good thing. The whole problem with most of our physics curriculum, from your school days onwards till even our undergraduate courses, is that we focus way too much on exact answers, and as a result of this, students very often have this completely wrong conception that approximations are things you do only if you can't do the exact thing, so it's a very bad thing to do approximations and you should avoid that as much as possible, and so on and so forth. That's complete nonsense. Approximation is the way you do science, all science, okay, and especially physics. You just do it in a controlled manner. That is, in this case, for example, if you knew that your RL is say smaller than R, would you trust your omega 0 calculation? The answer is you wouldn't. Then you would say, okay, connecting the RL is going to change the circuit way too much. I should not really expect to believe that omega 0 will be that. Okay, but if RL is 100 times R, then I'm pretty sure that using the omega 0 calculated without using RL will be fine. By the way, can anybody tell me what should the suppose I connected the circuit like this with the RL, unless the RL is not too huge, can anybody tell me what omega 0 should really be for this circuit with RL taken into account? Omega 0, remember, is 1 by CR if you ignored RL. Okay. So whatever your answer is, the answer should be such that when RL goes to infinity, remember, not 0. When RL goes to infinity, that means RL is not there at all, not connected at all. Then your answer should reduce to 1 by CR. Can anybody tell me?
1 by RL plus 1 by CR.
1 by RL plus 1 by CR. No, I mean omega 0. Omega 0 has to have dimensions of 1 by CR. Right? It can't be anything else.
1 by CR parallel RL.
Why do you say so? I'm not saying whether you're right or wrong. All I'm asking is, why are you saying that?
Sir, so basically,
Sorry.
if you just take the voltage like at the intermediate node as VA, and then calculate VO in terms of VA, and again VA in terms of VI, then I think if you do the calculation, then this is what comes out.
If you do the calculation, then this is what comes out is maybe correct. But I would say there's a much easier way of answering that. Especially after you've learned whatever you've learned so far, it should be easy for you to tell me what the answer is. The answer is correct. The answer is actually this. In fact, you should be able to guess that from the fact that if RL, for example, were very large, then R parallel RL would of course be R itself, right? When two resistors are in parallel, then the equivalent resistance is equal to the total equivalent resistance is equal to smaller one if one of them is much larger than the other, right? Is it okay? Sorry, there's a lot of stupid stuff all over my screen. Yeah. So, anybody who is writing something important in the chat, please speak up because I can't see the chat right now. Now, why do you think this is correct? And if you do the calculation, of course, you will get that. But there's a much easier way of answering this. Just think of it from the point of view of the capacitor. Let's put the capacitor outside. Outside, I mean just on the other side. I hope everybody recognizes that this is the same circuit, right? And the top one. Just switching the capacitor and the RL, of course, has not changed the circuit in any way, right? But now you can think of this as a black box with the capacitor sitting outside. And then what should you do? If you have something like this, you should simply use Thevenin's theorem. So this is exactly equivalent to this. Is that okay with everybody? And how much is R Thevenin? R Thevenin, remember, is nothing but what you see when you look in from this terminal after setting the input to 0. That is setting the input to its internal impedance. So if you short this out, what you get is R in parallel with RL. Now this is Thevenin's equivalent is something you should be able to see with one glance at the circuit. Okay. So in answer to Shashank's original question, if I put a resistance RL or put a circuit whose effective impedance is RL and use that to draw the voltage from the filter, the actual value for the cutoff frequency will not be 1 by CR, it will be 1 by CR parallel RL. If RL is say more than 10 times R parallel RL is almost R, so 1 by CR is pretty fine. Is it okay with everybody? Any further questions on this? I think I will switch off my camera so that the bandwidth is saved. So anything further? None? Okay, so now let me quickly ask you this. We talked about the AC bridges in the last part of lecture 7, right? And the idea essentially was it's very much like a Wheatstone bridge, except that you put in an AC input and from the output you use some kind of AC detector which we did not draw in the circuit there, maybe could be just a pair of headphones. Actually, in experiments it often is because human ear can make out sounds much better than say most of our cheap instruments. And the condition that we had was Z1, Z4 equals Z2, Z3. Okay. We also had an example of a few bridges. But can anybody tell me? Suppose I have a bunch of resistances and an inductance, and I want to measure, and a single inductance, and I want to measure the value of the inductance. How would I connect the circuit? By using an AC bridge like this. So what I have is a single inductance and as many resistances as I want. Of course, 4 I can put in 4 branches, but if you want, I can put in more. But all I have is a single inductance. Can I use the AC bridge to measure the value of the inductor? Any answers? So I can't see any response. So do you think it can be done at all? It may be possible that it can't be done. Do you think it can be done?
Sir, having only a single like inductor will introduce a phase that I don't think can be cancelled out by any of the resistances.
Okay, that's a great point. Of course, what you are really saying is something like this. This is the equation I have to satisfy. Z1, Z4 equals Z2, Z3, right? Now, this is a complex equation that of course means that not only do the magnitudes of both sides have to match, the phases also have to match. So complex equations of course really mean 2 equations, not just one. Okay. So now that you have Z1, Z4 matching Z2, Z3, the moment you bring in a single inductance, that will bring in a j omega impedance whichever branch you put in. So right now what will happen is 3 of the branches will have real impedances because you're only allowed to use resistances there, and one branch, 1, 2, 3 or 4, wherever, that will have a complex impedance, a purely imaginary one if you just put in the inductance, but also you could put in, say, maybe a resistance with it. So it could be j omega L plus R4 or j omega L into R4 by j omega L plus R4 plus maybe R5 or whatever. But the point is, one of the 4 impedances will be complex, the other 3 will be real. If that is the case, it's impossible to satisfy this equation because the phases, as was pointed out right now, will never match. Okay. So Z1, Z4 equals Z2, Z3 cannot be satisfied with only one inductance. So can I satisfy it with 2 inductances? Suppose I had L1 and L2. Then
So that's the Maxwell's bridge, right?
yeah, that's one of the bridges. In fact, the way these bridges are designed, essentially is designed keeping this in mind, that if you want to have a balance, you must have both magnitude balance and phase balance. So if you have 2 L's, when the L's have to go, they can't go, say the 2 L's cannot go to 1 and 4. If both L's went to 1 and 4, then you have the same trouble. Then you will have, then of course you have 2 complex numbers, but these 2 complex numbers both will have positive phases and will definitely not be able to match Z2, Z3, which will be a real number then. Okay. So it's not just a matter of a Maxwell's bridge having 2 inductances. It's important which arms you connect the inductances to. That's very much part of the design. Okay. So it's not just you throw together 4 arms with 4 components and you hope for the best. You have to actually take a conscious decision on what to put where depending on these issues. And of course, some of the bridges that we talked about, in fact the 3 bridges I talked about in the video, all of them had balance conditions which are independent of the frequency. Now since Z1, Z2, Z3, Z4 might very well depend on the frequency, usually will, right? If you have inductances or capacitances, then their impedances will definitely depend on the frequency. So it's very possible that you may have balance conditions which depend on the frequency. Now, such bridges may be more useful for measuring frequency than other purposes. Suppose in that case, maybe you might even use known components L, C, etc. and then just use it in such a way that it only balances out when the frequency reaches a particular combination of LCR and so on. And then by adjusting your variable inductance or capacitance or whatever component, you can actually measure the frequency using that. So these bridges are used for measuring components. It's also used for measuring frequency. And in the video, I just talked about the balance condition. What I did not really talk about too much was how useful each bridge is. Because then the question really would be several things. Is the bridge easy to balance? Those of you who have done Wheatstone bridge in your lab, most of you have, right? You would know that it's pretty easy to balance. There's a very simple standard rule to follow. You know when it deflects when the galvanometer deflects to the right, you know you have gone too high. Because it deflects to the left, you know you have gone too low. Then you essentially carry out the bisection procedure until it does not deflect at all. But that's because you have only one balance condition to maintain, and you can maintain that by just flipping one resistance, or changing one component. An AC bridge is typically much more difficult to balance than that. Of these, some AC bridges have balance conditions. For example, I forget the name of the bridge, but it's there in the video, which I forget which one. Has a balance condition which looks exactly like the Wheatstone bridge balance condition, R1 by R2 equals R3 by R4 at all frequencies. For such a bridge, what you could very well do is first start with a DC source, not with a sinusoidal source, but with a DC, and balance the bridge with the DC. That will actually help you to maintain one of the conditions fixed. Then you modify the other parameters. Okay, then you of course switch the DC source, bring in your AC source, and then you modify other parameters to maintain the balance to get the second condition right. And then of course there's the issue that if you're how sensitive your bridge is. Of course your bridge will give you exact zero when the bridge is balanced, but if you move away from balance, does your bridge show a big output, or does it still keep on showing a very small output? In which case, of course, if it's very small, then it may not be possible for you to pick out whether you moved away from balance. So there are all these other situations which go into deciding which bridge is better. Not all bridges are equally good. Okay, any further questions? Now it seems that nobody has actually taken a look at the diode video at all. Have you? At least. Most of you haven't. I know, I can make that out. That's fine. It's early days yet. But I was expecting a lot more questions from that video for the simple reason that the things that I discussed there are A, much more complicated than the electrical circuit part, and B, I really lied a lot throughout the video. That is, okay, I also said explicitly that I was lying. Okay, maybe not, I did not perhaps use the word lying so much, but I was hand waving all the time in the sense that I was trying to get the point across and sort of give you the feeling of what's going on rather than saying everything precise at the stage, for the simple reason that the amount of solid state physics, quantum mechanics and statistical mechanics you have to know in order to understand even something as so-called simple as the semiconductor diode is, well, a lot more than you know at this stage. And the funny thing is, at least, okay, the good thing is you can understand the action of the semiconductor diode rather well without going into all the details. And even the crude picture that I've talked about in the video, that sort of gives you the answer more or less correctly. So there are, so I derived a formula at the end for the current through a diode. Is that exact? Of course not. But does it give you the right picture? Very much so. Okay. So the next video, of course, will start from there. We'll treat the diode as a circuit element whose behavior we know and then talk about how to use it in various contexts. But has anybody seen that video? And if so, are there any questions from that? Of course, if you have questions on the AC part, that's fine. But it seems people have yeah, go ahead.
I have a few questions. Firstly, I couldn't understand like how the temperature gradient acted for the negative mass particles to move towards from the valence band to the conduction band. Like if a temperature gradient is there, you said that the negative mass particles would move away from the poles. So I don't understand.
No, I didn't say temperature gradient at all. I think you misheard.
You said that
electric. I said electric field.
So you said any disturbance, electric or
no? I think you okay. Sorry, I should have been more careful in picking my words. I said two things one after the other. You perhaps connected the two. I said a conductor is something which responds to external stimulus. Okay, that would mean if you're talking of electrical conductors, it responds to electrical fields. If it's a thermal conductor, it responds to temperature gradients. In both cases, the response can happen because an electron can change its state and go to some other state. And for that, it's essential to have empty levels nearby. When electron does not have empty levels nearby, then even if you have lots and lots of electrons, those electrons will not take part in conduction. Is that okay?
Yes, sir.
Okay. So that was one point. So after this, I did not talk about thermal conductivity at all because that's an important topic, but that's not our concern. Our concern is primarily electric field and how a system responds to electric fields. Okay. So when we talked about how a negative, yeah, go ahead.
That means that the electric field should always be directed at a particular direction for electrons to move from the valence to the conduction band?
No. Oh, those are two things. That has nothing to do with electric field in the first place. Or it can, look, even if you don't have any electric field whatsoever, why are the electrons always in the valency band? Firstly, that's because electrons tend to, or any system tends to minimize this energy, right? So what will it do? Electron will try to go to the lowest available energy level. Now, if electrons had been bosons, then they would have perhaps best liked to stay all of them in the ground state. That would lower the energy as much as possible. But electrons are not bosonic, they are fermionic. Because they are fermionic, what happens is electrons cannot all go to the ground level. One goes to the lowest available energy level, the next one goes to the next available energy level, and so on. And so this way the whole thing builds up. So at absolute zero, when there are there is no thermal energy, it's not temperature gradient we are talking about there. We're just saying if there is no thermal energy available at absolute zero of temperature, the electrons will just get to the minimum available energy configuration, which is filling up the lowest energy levels first and slowly rising up until a top level is reached, until all the electrons have their energy levels. Okay. Now, when this happens, actually two things can happen. One is the topmost level may end up being partially filled. Okay. So, after all, there will be some bands which are completely filled. So you have remember you have bands, then gaps, then other bands, then gaps, other bands, and so on. So electrons just keep on filling up all the bands starting from the bottom, and at absolute zero, there will be no gaps. All the lowest energies will be filled first. And then you will reach a situation where the top level is reached. Now, is the top level completely filled? That is an important question. If it's partially filled, then that material is a conductor. Okay? Why? Because that material has electrons in whose immediate vicinity near the top of the, okay, this top is called the Fermi level, named after Enrico Fermi. And this Fermi level electrons which are very close to the Fermi level, they have available empty energy levels just beyond that. So even a small energy which comes in from outside can help an electron to jump from one level to another and hence respond. Okay, but that's because this is all happening within a given band. The band is not filled completely. There are empty levels within the band and the electrons can just move. Okay, so that's one situation. That's for the conductor. The insulator and semiconductors are situations where the final level at absolute zero is completely filled. So you have a completely filled level which you call the valency band, and then you have an empty level above that which you call the conduction band. Okay, so a valency band completely filled, a completely empty conduction band, all this is at absolute zero. Now when the temperature is raised a bit, the rising temperature is not the same as temperature gradient. Temperature gradient means different parts of the system is at different temperatures. Here we are just heating up the system. So the system is not at absolute zero any longer, it's at a slightly higher temperature. Then what happens? Now thermal energy is available, so the electrons no longer necessarily go to the lowest possible energy level. Some of them have enough energy to jump onto the higher levels. Yeah.
Okay, so sir, let's say at 0 Kelvin.
Okay, I think somebody is complaining about the thing video is throwing down, so maybe I don't need the camera any longer, so I can just stop presenting. Okay, that might improve things a bit, but my network is pretty fast right now, so that should not be a huge issue from my end. But anyway, I don't need the camera any longer anyway. So yeah, so the next, what was your next question?
Yes, sir. So say at absolute zero temperature, I want to move in an insulator. I want to move the electron from the valence band to the conduction band. So I need to provide the electric field in a certain direction only, right?
No, okay. So if you want to move an electron from a valency band to the conduction band, that and you want to do it by an electric field, you can actually. But that requires a huge electric field. That's not the kind that you would usually have in a standard electronic circuit. Okay. So the mechanism by which electron hole, now there are several ways in which electron hole pairs are formed. That is, electrons jump from the valency band, go up to the conduction band. Okay. There are several mechanisms here, but what is important here is that the mechanism, all these mechanisms supply energy to the valency band electrons so that they can go up. The most obvious mechanism is just heat. So we move away from absolute zero, give the system some temperature, some non-zero temperature, and of course, usually we work at room temperature, so that's quite a long way from absolute zero. So you give the system thermal energy, quite a lot of electrons will jump from the valency band to the conduction band. That's one way. Another way could be to actually use very strong electric fields to drive electrons from valency band to conduction band. But when you say one direction, I think you are making a basic mistake. The valency band and conduction bands are bands in energy space, right? They're not in two different locations. So you can't do this by putting an electric field in a given direction. It's not as if you're making it go from one direction to another. Okay. You're actually trying to give the electrons more energy than they had so that they can go to another level. Remember, there's a gap. Without the gap, of course, any small amount of energy would have been able to push electrons from one state to another. But because there's a gap between the valence and the electron band, you need to supply a substantial amount of energy. Another way to supply energy would be light. So you shine light on say, when a PN junction, you might end up with producing electron hole pairs which will produce extra current. And that's the way photovoltaic cells work. So there are many other mechanisms beyond just temperature, but the most common mechanism is just give heat, and that will produce electron hole pairs. Now, once the hole is formed, The real question is, why does the hole behave like a particle at all? You have all studied this in class 12. You know that there was an electron there in the valency band, or used to say bonded in the covalent bond, perhaps. And now you don't have an electron, you have a gap. So a gap in a negative energy electron, negative charge electron, should be a positive charge particle. However, you have to also realize that this electron, if it were positive mass, then this gap should have behaved like a negative mass particle. That doesn't happen. You treat a hole as a genuine positively charged particle, in the sense that if you give a force, suppose you have an electric field in a direction, now you have an external electric field on a direction. Suppose once you have these conduction electrons and holes, now you put in an electric field. What will the electrons do? They will be pushed by the electric field. In which direction? Opposite to the electric field, right? Because they are negatively charged. And they will accelerate opposite to the electric field. Okay? What about holes? Holes, being effectively positively charged, should feel a force in the direction of the electric field. But if they were really behaving like gaps of positive mass electrons, then they would have behaved like negative mass particles. And because they would have behaved like negative mass particles, then they would have accelerated opposite to the electric field in the same direction as the electrons do. That would have been a bit of a disaster, because the two currents would have cancelled each other out. That does not happen. Both electrons and holes actually produce the same current in the same direction. Electrons move opposite to the electric field. Holes with the positive charge moves towards the electric field. Why? Because the holes actually behave like positive mass particles. And that happens because of this magic which quantum mechanics gives us, that near the top of a valency band, an electron behaves effectively like a negative mass particle. And that really means that if you just focused on an electron at the top of a valency band and gave it a force from outside in some direction, the electron would effectively accelerate in the opposite direction. Now, why does it happen? It happens because, remember, the force that you give is not the only force. The entire crystal is actually exerting its effect on the electron as well. So what you get to see is the sum total of all the effects. The external force you give and the force which all the nuclei and other electrons exert. And this is rather magical, and this is impossible to understand without quantum mechanics. That in a periodic potential, if you put an electron in a periodic potential, and if you subject it to some external force on top of that, the electron will respond to that external force almost exactly like a free particle, except with a changed mass. And that mass can even be negative. The final result is very simple, but the way in which this can be arrived at is rather, well, not very complicated, but it requires some amount of advanced quantum mechanics. And frankly, it's one of the miraculous results which quantum mechanics gives us. Classical mechanics would not have told you anything similar. But by the way, okay, this is out of context for this course, but most of you have heard of the positron, right? Haven't you?
Yes.
Yes,
Sir.
sir.
The antiparticle of the electron. So do you know how Dirac predicted the positron in the first place?
So with the negative solution of the E equals mc square, you mean the whole square relation?
Yeah, in a way, that's right. Well, basically what Dirac was trying to do was to write down the very first, well, not the very first, Dirac was trying to write down a relativistic equation for the relativistic quantum equation for the electron. And of course, relativistic mechanics allows energy to obey E square equals P square C square plus M square C to the 4. So any solution would have to give you that. But of course, that gives you both positive solutions where the energy is more than mc square, on negative solutions with energies less than minus mc square. Right? Now, in classical physics, that's not a problem. In classical physics, if you have an energy gap between plus mc square and minus mc square, then you would simply say that all particles have positive energy and they can't have negative energy simply because they can't cross the gap in between. But even from the amount of quantum mechanics you have studied so far, I guess 2 courses so far and another course going on right now, or maybe 1 course only, you've heard of tunneling, right? So if you have a forbidden gap between 2 allowed energies, an electron can actually go from one to the other. So relativistically, because the energies available are plus mc square or more for a free electron and minus mc square or less for a free electron, quantum mechanics allows the electron with positive energy to tunnel through and go to the minus mc square level or minus mc square below levels. And once it goes there, it should be able to keep on going down further and further in energy and keep on losing energy and essentially destroying the world in a fit of huge amount of energy. And unfortunately, Dirac's equation also had this. Every equation which ultimately is consistent with relativity should have these states, this negative energy states. So Dirac came up with this huge brainwave. He said that, okay, electrons are fermions. So why don't we assume that all the negative energy states are already filled up, completely full? Then of course there will be no possibility of an electron to tunnel inside because there are no available states. That's fine, but then you might ask, if we have so many infinitely many negative energy electrons, why don't we see them? The answer is we never see the background. We only see fluctuation from the background. So if the negative energy C is completely filled forever, you will never see it. So this was Dirac's solution to the negative energy problem. You really have negative energy states, at least in Dirac's version of the theory, and the negative energy states are completely filled. Now the problem was, another problem, the additional thing which came out of this was, if you supplied enough energy from the outside, it should be possible for a negative energy electron to jump to a positive energy state simply by supplying enough energy. So then you suddenly get a positive energy electron out of nowhere. But it's not out of nowhere. There's now a gap in the negative energy C. And there's a gap, the fluctuation which you can very well observe. And a gap in a negative energy C behaves exactly like a positive energy, positive charge particle. That was Dirac's prediction of the positron. Okay. So this was how he arrived at the positron. Now, the reason why I'm telling you this is that if you think of the electron hole picture here, electrons in the conduction band, holes in the valency band, it's exactly the same as the Dirac picture. Dirac used this in a relativistic context, where of course you had a vacuum, nothing, which was supposedly filled with negative energy electrons, and gaps in the negative energy C would be positrons. Here you have filled up valency band, empty conduction band. If you have enough energy, valency band electron may jump to the conduction band. Now it becomes a conduction band electron, and the gap in the valency band becomes a positive charge, positive mass particle. Just like Dirac's positron became a positive charge, of course, hole in a negatively charged thing must be a positive charge, but also positive mass, because all of these were negative mass particles or positive energy particle. That's it's better to say that. So in fact, the electron hole picture and positron electron positron pair production essentially the same mathematics, but this one in a non-relativistic context, but the same basic idea. In fact, frankly, many people would say Dirac's theory basically is the electron hole theory used for relativistic physics. The only problem with saying that is Dirac's theory came earlier. Electron holes came in only with semiconductors, which were a lot later into the picture. But it's the same physical principle. So the next video will be coming soon. which will be on applications of the diode, I will give you a much shorter problem sheet this time around, the next problem sheet, for the simple reason that you should spend more time looking at the videos and trying to understand what the issues are, because we are now getting into much more complicated territory than your previous courses. Okay. So I'm out of time, but if anybody has a quick question,
sir.
yeah, go ahead.
This is not a question, but this is just a concern a lot of us were discussing. Usually when you show us the video via camera, it takes up roughly 3.1 MB per second. And that becomes a huge amount for all of us because most of our data packs are like 2 GB per day, etc. So would it be possible for you to do something about it so that the data consumption is slightly less, keeping in mind
that I understand, but that is the reason why I am keeping these discussion classes to once a week. Unfortunately, without the camera, a discussion class becomes very difficult because I have to anticipate whatever you're saying, right? When I'm showing you a video, I am deciding what to say. So I just do that beforehand. I make it. So there at least I can have a those are much smaller in size. Primarily because, first of all, you don't get to see my face. The reason why the camera takes up much more bandwidth is not so much because of the camera, but because things are changing. And if I could write without my hand coming into the picture, perhaps your video would have consumed less. So we'll try to use the camera less, perhaps. But unfortunately, I have to keep on talking to you. And just talking will not work. I'll have to change things a bit. So let's see. If it's just equations, I can manage on the screen. But if it's also circuit diagrams and so on, doing that real time without the camera will be difficult. So I will try to at least reduce using the camera. Okay, but that's the reason why I'm not taking 3 classes a week. I would have loved to take 3 classes a week. That would be better for me and perhaps better for the class. That is without putting up videos and so on. I appreciate your point, but unfortunately there's not much I can do about it. I can't completely leave out the camera, but I'll try to reduce its usage. Okay, at least right now when I was not using it, it was still switched on. I can of course, but by the way, if I'm not using it, it will not really add much to your bandwidth.
But not exactly, sir. It still showed 3.1 MB per second.
No, that might be basically because it's showing an average rather than instantaneous values. Because the way in which most of these algorithms work is that they actually transmit video changes. They don't transmit videos, which is precisely why switching off my own camera reduces the band size a lot. The camera which shows my face, for example, my face moves a lot more than the page on the paper. But even then, I agree that this is actually consuming more bandwidth than it should. So at least when I'm not using it, I should keep it switched off. So please remind me of that.
Thank you, sir.
Okay, I will try to see whether a tablet actually reduces the usage. It perhaps would. Let's see. I will try to get that next week. Let's see. Okay. Anyway, thanks and bye.